Let's talk about displacement current using an example. All right, remember Ampere's law. We get that new extra piece on there. H dot dl is total enclosed, we're talking about closed path here, enclosed current. This is surface integral of conduction current density, J, plus this other thing that we learned about last time, displacement current density integrated over that surface bounded by this path. Okay, I'm going to draw this out, and you'll see something kind of interesting, that all that matters is the surface has to be bounded by the path that you're doing this H integral. And my favorite example here, and the one that we use a lot in chapter 9, is a wire connected to a capacitor. And when it's DC, no current's going to flow, but when it's AC, you have current flowing through here, and it's going to pass through this capacitor, and the impedance of the capacitor is going to decrease with increasing frequency. We're all familiar with this from circuits class. And now I'm throwing this magnetic stuff and going, let's do a path integral around this purple loop. Okay, and I can figure that it's going to be symmetric. I can start using it to figure out H. The larger picture here is I'm going to get some number out of this, H dot dl, and it's going to add up to the surface integral of these two quantities. Here we've got conduction current density when we're in the wire. Okay, when you integrate up current density, you're getting current in amps. Okay, so that would give you I. But when you're in the capacitor, if instead of drawing a surface that passes through the wire passes through the surface, I should say, what if your surface kind of bubbled out? You're allowed to do any surface you want. And so I bubble out my surface so that it goes through the capacitor instead of through the wire. And here the conduction current is 0. Okay, but I've got a changing electric field inside the capacitor. So I've got to get the same result, because on this side I haven't changed anything, I've just got my purple loop. Okay, so it's kind of interesting. And from continuity and talking about the circuit laws, we know that the current going through here in time harmonic current, is this sine omega t type thing, is going to be the same as the current that's going through here. They're all in series. Okay. Need another marker here to get through this one. So we can do an example with just a capacitor and look at this one. Okay. What's the displacement current? I'm not talking about displacement current density. I'm going, if you've got a capacitor and it's got a gap of 3 millimeters, and you've applied a voltage to it. You've put one side at ground, and then the other side you put a 50 cosine omega t AC signal on. You're going to get some energy dissipation in here. You could probably put a resistor on here. You got a little RC circuit. Okay. And you're going to be able to solve for the total conduction current by thinking about this as a boundary value problem like we did in chapter 6. Okay, so somehow turn that into an electric field. How do we do that? We remember that the voltage or the electric field in the capacitor is, if it's parallel plates and they're a lot closer than their width, D is much less than W. The electric field in that capacitor is pretty much uniform. Okay. And we have to use that information. We can get, and we can also think about the units of voltage and the units of electric field. So electric field is volts per meter. So we're going to get 50 cosine omega t over 3 millimeters. And to be perfectly formal, we'll put a little z hat on it. Okay, and it's changing with time. I'm not going to put a sign on it. And we can take a epsilon of the material in here. This material's permittivity, the filler of the capacitor, whatever that permittivity is, D is epsilon E. And so when we boil it down to a specific problem, epsilon 50 cosine omega t we had over 3 millimeters, then we can take a time derivative. Okay, we're just going to get omega and a sine term in there. And so this is one of the examples that we work out. This is going to give us the conduction current density, J sub D, dt. If we wanted to figure out the total conduction current, or displacement current density, we have to integrate J sub D over this area. And again, going from our experience in Chapter 6, solving the boundary value problems, everything was pretty uniform in these parallel plate systems. You know, we're able to think of it as a kind of an infinite plate. When things are really close together, we're able to do that. So we can take this result by taking the time derivative and just multiply it by the surface area and get the displacement current in amps.